Assalamualaikum and a very good day, everyone. So today I will continue our lecture with the third topic in your textbook with the title Laplace Transform. Okay, so let's recap the last topic or the last lessons on the theoretical model. So basically from the topic number 2, we have looked at the dynamic. We have derived the dynamic models for this blending system. Basically we can actually derive equation where from this model, basically the mathematical models can be developed to describe the dynamic operation of this blending system. Okay, so in general we can say that by finding the output variable, as a function of time for some change in the input variable. For example, this equation we have this output in function of time, by varying some parameters, for example x, and then this equation, when we look at this example, we have this equation. So basically to solve this equation, we need to use some methodology, some mathematical operation, and this equation usually we call it as ordinary differential equation. And one of the mathematical tools to solve this ODE, we call it as a Laplace transform. So basically in this topic number 3, we will cover on a Laplace transform technique, where Laplace transform is one mathematical tools, which are important analytical methods to solve linear ordinary differential equations. So basically for application of nonlinear ODE, first we need to do linearization. So this Laplace transform can transform ordinary differential equation into algebraic equation, and it play a key role, important key role in process control concept and also techniques. For example, in a transfer function, later on we will look on what is transfer function, frequency response, control system design, and also stability analysis. Okay, so now let's look at the definition, the definition of Laplace transform in the expression. So Laplace transform can be written in this expression where capital Fs, Fs equivalent to L, capital L, and then in the bracket we have a function of time, and then equivalent to this expression. Okay, in the textbook it's labeled as equation number 3, 1. So you can see each of this expression to understand on what is the definition for each expression. So capital F in the bracket S is a symbol for the Laplace transform, and then capital L is a Laplace transform operator. Okay, here we have Laplace transform operator, and then Ft is some function of time, and S is a complex independent variable. Okay, basically if you look at this expression, you will not understand anything, but after we do some example, then you will understand. Okay, so this L operator transform a time domain function into S domain function. So if you look at this expression, basically it changed this Ft into Fs. That's what the common or what the Laplace transform do. Okay, now we look at the inverse Laplace transform, L inverse, L inverse. So by definition, the inverse Laplace transform operator, we write as capital L, and then we have like power of -1. Converts an S domain function back to the corresponding time domain function. So this is the general formula for inverse Laplace transform. So Ft inverse Laplace symbol, and then we have capital F in the bracket S. So there are some important properties, for both Laplace and inverse Laplace are linear operators. So it will satisfy the superposition principle. So what is superposition principle? For example, we have this expression axt plus byt. Then we take Laplace for this expression, and then we take out the what we call it, the constant. For this expression, a is constant, b is constant. So we take out both, okay, a, and then write again the Laplace operator plus b Laplace operator for another second expression. Okay, so from here we can by doing this Laplace, then we will get from xt, convert xt into xs. Okay, from expression t function to s function, right? So we can write into this expression. Okay, so this xt and yt are arbitrary function, okay, and a and b are constant. Then actually we can write similar, okay, if we put the inverse Laplace into this expression in the form of xs and ys just now, and we can say it's similar with expression with a function of t. Okay, so this is called as the superposition principle. Okay, now let's look at several common functions which usually appear in a function. Okay, so that we know how to solve all this kind of function. So the first function is called as constant function. Okay, let's look at what is a constant function. Constant function is when you have ft equivalent to one constant, any constant. For example, in this case, we have a constant. We just put as a, yeah? So then, from the definition of the Laplace transform in equation 3.1, we understand this is the expression for Laplace transform, right? Okay. So if we have this kind of function, ft equivalent to a, then we can write the fs is equivalent to a over s. Okay, you can see textbook how it derive the Laplace for constant until it get this expression. But what I want to tell you, the output of this expression, basically for any constant, we just the Laplace transform is equivalent to a over s. Okay, just remember a over s. Okay, so this one is for constant function. The second function that usually used in the control system is called as step function. So what is step function? If we have this kind of expression, okay, I think this is very familiar for you. Okay, usually we have one function which equal to two numbers, two constant numbers, with a condition of this. Okay, if you look at this graph, if the t is less than 0, okay, t less than 0 means at this point, okay, t less than 0, the st, the expression will become 0, means the value is 0, right? And then if the t is greater than 0, means this line, so if greater than 0 means the function will become equivalent to 1, so it will become 1. So this is we call as a step function. It has one step function. So for this kind of expression, how do we do the Laplace transform? Because the step function is a special case of constant, so it follows from equation 3.4 just now. So basically for this step function, it's equivalent to 1 over s. If you look at 1 is actually basically similar to a. Okay, for constant function just now we have a over s, right? So similarly for step function, basically the expression is similar to the constant a over s, but in this case we have 1, so just put 1 over s. So please remember, for step function, the Laplace transform is equivalent to 1 over s. Okay, let's look at the next one. Okay, we have a derivative expression. This is a very important transform because derivative appear in the ODEs for dynamic models very frequently. So let's look at this general expression for derivative. Okay, so this is derivative, the Laplace transform of derivative. So if we have this kind of derivative differential equation, so if we convert into Laplace transform, it will become like this. What do we understand from here? We put s and then f s minus f0. So what does it mean at the back? It's actually when the time is equivalent to 0. So we have to put some value at the back minus this function when the time is 0. Okay. Similarly, for higher order derivative, if we have like d squared d to the power of 3, which called as higher order derivative, this one is d1, right? Only one, so we don't put this one, so df over dt. If we have higher order like d squared f over dt squared, so we can expand the equation into this expression. Okay, if you look at here, for example, we have d squared, so you have s squared fs minus s f in the function of 0, t equal to 0, and then minus s to the power 0, basically f1, f0, this one is f0, yeah. If we have if n is equal to, okay, if n equal to 2, so we have this one is f0. So we'll stop until here, I think. Yeah. Okay, we will stop until here. So this is how we write the expression for higher order. We have to consider when the initial condition at time time equivalent to 0. Okay. So n is an arbitrary positive integer. Okay, we have positive 1, positive 2 means the derivative in positive integer. Okay. Okay, when we have all initial condition 0, which equal to 0, t equal to 0, f, when you put 0, it equal to 0. So what happened? So basically, the equation just now can be simplified into this general equation. In condition where the all initial condition are 0. Okay, then we have this general expression. And in process control problem, we usually assume 0 initial condition. But if the question give the value, you have to consider. Okay, this condition if the f0 is equal to 0. Okay. Okay, the next function is a trigonometric function. So basically in process control, trigonometric function, uh, where we have t as the function of time is usually also commonly used in a process control. So how about if we have a trigonometric function? Basically, we can solve by using integration or by parts, or alternatively, we can use Euler identity. So by deriving all this equation, trigonometry, and convert it into Euler number. Okay, so we have here Euler number, and after derivation on this Laplace transform, then we will obtain this kind of function, yeah, for trigonometric function. So this is we call as we use a Euler identity function, okay, for trigonometry. So for example, if we have cos wt, if we use a Laplace transform for cos wt, we must choose the fs equals to this one. Okay, s divided by s squared plus w squared. So for sin, for tan, and another trigo function, then later on I will show you in the table, the summary table. Okay. Okay. Finish about trigonometric function. So what else we have? We also have exponential function. I think exponent function is very familiar for you. So this is the example of exponential function. Okay. So basically, if exponential, what can we derive here? By deriving Laplace transform for exponential, then this we come up with this general expression for exponent, 1 over s plus b. So b is actually the 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 constant you have in front of t. Okay, like this one. For example, this one. Okay, so if for example, if you have exponent negative 2t, so the expression for the Laplace is 1 over s plus 2. So this is just example, yeah. So that means B is the front of the t function. Okay. All right. So that one is for exponential. Okay, the next function is called as rectangular pulse function. So what is rectangular pulse function? Okay, I think in control system usually we are very familiar with this kind of graph, yeah. For just now we have a step function. In this case we have rectangular pulse. It looks like rectangular. Basically, it's look like this, yeah, like this. Okay, 0, and then you have one step and come back to 0. This is very common in process control. So actually this kind of graph depict the opening and closing of valve regulating the flow in the tank. Okay, if you have this kind of control system, you need to have this function is called as rectangular pulse function, and mathematically it will return as this function, okay, where we have this function with three step. Okay, the first one is when the condition is 0 at this time range, and then we have function h. So what is h? H is the height of this step, and tw is the width of the function. Okay, so and then it comes back to 0 when apply this condition. So this is called rectangular pulse function. So for rectangular pulse function, we're taking the Laplace with the h function we have here, the height of the step. Okay, by taking this, then we can come out with this expression. All right. So if you have Laplace transform, you need to Laplace transform for this h equation or h expression. Then the expression for the Laplace is given by this. Okay. So in this expression, we can see that we have TW. TW is the width of this pulse function. Okay, the next one is impulse function or direct data function. So what is impulse function? Okay, just now we have rectangular pulse. So when we have a condition or the limit for the rectangular pulse, then we call it as a impulse function or direct delta function. So for this case, we're taking the limit, okay, to the rectangular pulse function just now. Okay, when we have limit, then we usually the function is written in the form of this symbol we call as direct delta. Yeah, direct delta. So when by taking Laplace to this direct delta, and finally we come out with the expression of A. That means if you have to Laplace, okay, you have to Laplace transform for any expression, for example, A constant multiple with the delta function, direct delta function of expression, then the expression is similar to when you have A only. Okay, so this is the expression or the Laplace transform for impulse functions or direct data function. Okay, so now let's look at okay, this one is already. So now let's look at the solution of any ODE using Laplace transform. So we have a basic step where first we need to take the Laplace for both sides of the ordinary differential equation first. The second step is to rearrange the resulting algebraic equation, the S domain, okay, S domain, to solve for the Laplace of the output variable. For example, we use Y capital and in bracket S, okay. And the third one is to perform a partial fraction expansion. Later on, we will see what is partial fraction expansion. And lastly is to use the inverse Laplace to revert back into yt. Yeah, yt. Just now we from xt to ys, and then we try to convert into yt from the expression for ys. by using the inverse Laplace. So these are all the simple 4 steps to convert to solve this ODE, okay, ODE expression using Laplace transform. So this table, okay, summarize all there are so many type of function that we discussed just now. So this table summarizes everything. The conversion of ft into fs. Okay, so you can refer to this table for the given expression. Okay, so this is the continue from the previous one. In textbook, you can also see this table. The number is table 3.1. Yeah. Okay, you can take a look. Okay, so we have about 26 expression. Okay, so let's look at this example. Okay, for example, we have this expression, okay, this function 5 dy over dt plus 4y equivalent to 2. And we have this condition y, initial condition where at t0, the function is equivalent to 1. Okay, so how do we solve this expression in control system? So what we can do is following the previous step mentioned just now. So the first step is to take the Laplace for both sides of the ODE. Okay, so we need to take Laplace both sides. Okay, so the first step is just put Laplace to all the expression. 5 dy over dt plus 4y equivalent to, okay, just put the big bracket. Okay, another Laplace, this is the symbol of Laplace, put another big bracket of 2. Okay, the first step is to take Laplace for both sides. Okay, take Laplace for this side and take Laplace for this second side. Okay, and then after you do like this, you can actually split. Okay, split the Laplace. For example, if you have this operation plus, then you can split into 2 Laplace form. So what happened is, so you can break it into this one, 5 dy over dt, okay, plus, just put another Laplace transform for y. Okay, equivalent to, okay, this just remain because it only have one expression, 2. Okay, all right. After you have you break the certain function, then you can actually take out all the constant value. For example, we have this 5 dy over dt. You can take it out. Okay, take it out the constant. Similarly with this the second expression. Okay, for example, take out the 5 the constant and put the Laplace again. So it will look like this. Okay, so that easy for us to see the function. Okay, the function clearly, what kind of expression we have in the bracket. So like this, equivalent to Laplace 2. Okay, now as you can see here, you can see clearly what type of function you have. In this case, you have derivative, right? Derivative. This one you only have a function of a simple function, and this one is a constant. Is it correct? Okay, so when you identify type of function in the function, in the ODE function, then actually you can solve it. Okay, so in order for you to transform it into S function, so you can see, you can refer my previous note on a derivative. For example, dy over t is derivative, so you can look again, derivative. So basically derivative derivative. Just now we have derivative. Okay, this derivative. So in order for you to write derivative, the expression must look like this. So the Laplace transform of any derivative is equivalent to this expression. So you just follow. Okay. In this case, it use f, but in your case just now, it use L dy per dt, right? Dy over per dt. So you just follow the how it writes the expression. So put s, and then if this one is use f, you use y. Okay, capital Y, and then just put s, and again minus this one f, you put y 0. Okay, so this is how you expand the expression just now in the question previously. So for dy over dt, so this is how we write. Okay, simple, very simple. So okay, so for this case, you can write like this. How do I just put the constant in front? So the Laplace transform of this one equivalent to s capital Y in bracket s minus y 0. Close the bracket. So for this expression, we already solve the Laplace into this. Okay. So moving on to the next second expression, which is 4y. 4y. Okay. So we already solved for the first expression. Our second expression is for Laplace transform expression y. So for y, you just write this way. Okay. So basically plus still remain the constant 4, and this expression is equivalent to y capital Y s. Very simple. Okay. So this Laplace of y is just equivalent to capital Y s. Okay, and the next one for Laplace constant. Still remember the first expression I mentioned just now for constant, what happened to the Laplace? Okay, we can see. Just look back in the notes. Okay, wait here. Okay, this one. So basically for constant, we already know for any constant, the Laplace transform equivalent to the constant itself divided by s. Okay, so what can we do here is, okay, so for number 2, so this is assumed as a is equal to 2. So what happened is the Laplace transform of this one is equivalent to 2 over s. See, so this is the first step you take to convert to Laplace both side into both side with the Laplace, and then write the expression in terms of ys. Okay, so after you finish this one, so the second step, let's look at the second step. The second step is to rearrange the resulting algebraic equation in the S domain to solve for the L of the output variable, for example, ys. So make it the equation into ys. So what you will do is rearrange this equation. Okay, that means but first in the question already mentioned the initial condition where y0 is equal to 1. So actually from here you can substitute into 1, right? So this one is equal to 1. Okay, so if I write again this expression, let's have eraser. Oh, I cannot erase this one. Oh, cannot erase, it's okay. Okay, I write here. Okay, so you can simplify into 5 in the bracket s y s So this one is equal to minus 1, yeah? Minus 1 plus 4 capital Y S equal to 2 over S. Okay. So if we rearrange this expression, so what do you get? You will get YS equal to, so get the expression in terms of YS. Okay, so I just write again this one. Okay, so basically you will get this after you rearrange the expression into YS. Okay, and what happened after that, as the next step is to, the third step is to perform a partial fraction expansion if needed. Okay, if the expression need you to do the partial fraction expansion, then you have to do it. And the last one is to use the inverse Laplace to get the expression into yt again. Okay, so you have to convert it into yt expression. So what is the next step is, okay, so you have already this expression. So if this expression need for you to solve a partial fraction, then you have to follow the partial fraction. And if no, just proceed to the inverse Laplace. So you can do the inverse Laplace for this expression to get it, to convert it into what we call it, into yt again. So this one is fs plus 2 divided by s 5s plus 4. So just follow the step slowly, okay, step by step, so that you don't miss any marks. Okay, so just follow all these 4 steps one by one. Okay, by taking this inverse Laplace, okay, actually you can refer how can we convert this. So this basically will convert into yt. So how do we convert this expression into yt? Okay, you can refer to this table. Okay, all this expression that I told you just now, we have about 26, yeah, 26 expression of function. So you can always refer to this. Okay, so in this case, so yt, okay, so in this case we can see that from the table 3.1, this equation is very close with number 11, yeah. If you look at the expression of fs, okay, we can refer to the fs first. Okay, because this one we want to convert from s into expression t, so we have to look at the right side. Okay, the right side in the table. So if we look at this equation, is almost similar with this one. Now you have to find the suitable, the equation that fit to your equation in order for you to get the expression in t. So if you look at the number 11, it's very close to this one. So basically, if you change this one, how to get this expression similar to this one is, okay, if you look at here, the expression is s plus b3, right? So you make it this equation similar to this one. So this expression need to divide by 5, right? So you have to divide everything with number 5 in order for you to get s. So the expression will become like this: s plus 2 over 5, because we divide everything with 5. So s 5 divided by 5 is 1, so we left with s only, plus 4 over 5. Okay, so from here you can identify what is b1. Okay, if we try to make it similar, so b1 is equal to 2 over 5, b2 here, so b2 is 4 over 5, How about B3, B1? Oh, sorry. I think this one is B3, yeah? B3. Because up here is B3, so this one is B3. So B3 is 2 over 5, B2 is 4 over 5. How about B1? B1, if you look here, B1 is here. So here we only have S. So basically B1 is equal to 0. Okay. So by identifying all this expression, then you can actually convert it into this expression. So what we have here is, you can try yourself. So we will get, so this is the solution here. You can also refer to the textbook. So this is the final expression in expression t, yt. So 0.5 plus 0.5 exponent negative 0.8t. So this is the final expression in terms of yt. Okay, just now in all the step for Laplace transform, step number 3, we can see I did mention about partial fraction expansion. Okay, this occur when you have high order denominator. Okay, denominator. So the basic idea is to expand a complex expression of y's into simpler terms, each of which appears in the Laplace transform table. Then you can take the inverse Laplace of both sides of the equation to obtain yt. For example, if you do the Laplace transform and suddenly the ys is become like this. Okay, like this, meaning to say that you can see that the denominator have higher order. So how do you solve this equation? If you look in the table, there is no no expression for this one. So you need to simplify, or you need to perform a partial differential or partial fraction expansion first. Okay, so you need to perform partial fraction expansion. So this is how it's look, okay, for partial fraction expansion, where you split, okay, you factorize the bottom one, the denominator, with a higher order. So you factorize into this expression, s plus 1 and s plus 4. Okay, so if we rewrite this equation, and we put into these terms, or this expression, where alpha 1 over s plus 1, split it into 2, plus alpha 2 divided by s plus 4 for the second uh, factor. The first factor we put alpha 1, the second factor we put alpha 2. Okay, so this is how we start to do the partial fraction expansion. And the next step, okay, so this coefficient alpha 1, alpha 2, we have to determine. So how we determine the alpha 1 and alpha 2? We have 3 methods. So the first method, we just multiply both sides by s plus 1, s plus 4. Meaning to say, you want to make sure that this denominator is can be cancelled out. So we multiply both sides with this expression. So what happened? If we multiply both sides with this expression, then you will get this equation. Okay, this equation. So from this equation, basically you can simplify. Okay, if we try to solve this one, s plus 1, you solve for the right side one, and you will get like this here, a1 plus a2s plus 4a1 plus a2. Okay, so equivalent to s plus 4, s plus 5 just now. So if you look at here, we make it similar. So this represent s, and this is represent this 5. So you will get a1 plus a2 equivalent to 1s, and the second term is 4a1 plus a2 is equivalent to 5, the second number 5. So we get these two expression, and then we can solve. When you have these two equation, then you can solve for alpha 1 and alpha 2 simultaneously, and the expression give is alpha 1 is equivalent to 4 over 3, and alpha 2 is equivalent to negative 1 over 3. Okay, this is the first method you can choose. And the second method to solve alpha 1 and alpha 2, we can specify any two value of s. Okay, just randomly put any value of s. For example, s equivalent to -5. So what you get? The alpha 1 and alpha 2. So you will get the first equation. The second one is you just just put it into another value and you will get another expression or equation. Okay, so from this, when you do solve simultaneously, then you will get another the value of alpha 1 and alpha 2. Okay, so this is the second method. Let's look at the third method. The third method is called as Heaviside expansion. I think the most easiest way is by using Heaviside expansion. So what you do is, for this kind of method, first you need to find alpha 1, multiply both sides by s plus 1 and let s equivalent to -1. Meaning that you take this one as your reference, okay, and then you multiply both sides with this expression, and because it's s plus 1, so when you put it s plus 1 equal to 0, so basically s equivalent to -1. So you put this condition as well, okay, and by substitute into this expression, okay, then you will get alpha 1 is equal to 4/3. Mean to say, if you multiply both sides with s plus 1, okay, multiply s1 plus 1, so automatically they will cancel off, right? This one also cancel off because here you also s plus 1. This one s plus 1. So, and then s you substitute into -1, all -1 until you get alpha 1 is equal to 4/3. And then to get alpha 2, you multiply both sides with s plus 4. You take another denominator, s plus 4, and let s equivalent to -4, and you will get answer for alpha 2. So this is called as a Heaviside expansion method. Okay, so basically for partial fraction expansion equation, we can put it into general expression like this. Okay, as you can see just now, basically ys can be written into this general expression where we have ns divided by ds as the denominator. Okay, so this denominator is usually can be expressed into these terms. Okay, so here ds is an n-order polynomial with the roots of s equivalent to -bi. Okay, if we put s plus bi equal to 0, then s equivalent to -bi. All being real number which are distinct, so there are no repeated roots. So the partial fraction expression is equivalent to this general expression. So if you want to solve a partial fraction expression, you can always look at this general expression. So this ds, or the denominator, is called as characteristic polynomial. But there are some special situation when the denominator, okay, sometimes cannot be factorized. Okay, so usually we will solve using complex roots. Okay, still remember how to use these complex roots. These complex roots, when you cannot factorize the denominator, and another case when you have a repeated roots. Okay, that means the value of b1 equivalent to b2 equivalent to -3, meaning to say that s plus b1 bi, for example, it has a power like this, so we call this as a repeated roots. So for this situation, the PFE has a different form. So basically this is the representation. Okay, so this is the representation. So let's look at the one by one. Okay, for complex factor, the complex factor can be write like this. Okay, so here is the denominator cannot be written as the product of two real factors, but which can be determined by using quadratic formula. However, we can obtain the factor by completing the square. then it's possible to rewrite denominator in form of two complex factor as I mentioned just now. So you can write into this equation, yeah. So if you have this denominator which cannot be factorized, you have to convert it into this expression. S squared plus d1s plus d naught equivalent to s squared blah 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 blah. Okay, so this is the general expression. Okay, after you convert it into this s plus b plus jw, s plus b minus jw. Okay, and then if you look at the b value here and w can be expressed in these two terms. Okay, after you know the b and w, so basically you can find the value. Okay, but for the ys you can change into this expression. Okay, so if you have this equation, you can split it into these two, and then you get this kind of equation. So from here you can solve for alpha 1 and also beta 1 as usual using partial fraction expansion method. Okay, so this is complex factor. So let's look at this example. Okay, as we look just now for this factor, this expression or this equation, basically it cannot be factorized. So what we do is you have to convert it into a complex factor. So if we use the previous formula, we will get these two, s plus 2 plus j, s plus 2 minus j. So from this, you can rewrite into this expression as I mentioned just now. Okay, where we have in the form of okay a1 plus jb1. Okay, in this form we will use a3 plus jb3. Why 3? Because this one and this one represent the other two expression, yeah, the other two expressions. So this one is start with 3. Okay, so this is how you solve for a complex factor. And then after that you can solve using Heaviside expansion to get all this value alpha 1, alpha 2, beta 3 and so on. Okay, so we have another thing. The second one is repeated factor. Repeated factor, if a term s plus b occurs r times in the denominator, where the r terms must be included in the expansion that incorporate the s plus b vector. For example, we have this. Okay, for example, we have this expression. If you look at this expression, if we try to factorize or simplify it, we will get s plus 2 squared. When we have squared, so in order to solve this, you must write the r term first. Okay, you must write the r terms, meaning to say you must split it into a1 s plus 2, then you can put it into the squared terms. Okay, so don't forget to put in a single term and then follow the second term. Okay, so this is how you write for the repeated factors. And then after that, you can just solve using Heaviside expansion or other methods to solve for alpha 1 and alpha 2 and alpha 3. Okay, so this example 2, okay, solve the ordinary differential equation given with the given initial condition. So I think to prove that you are watching this video, I hope that you can do this example, and then please upload the the your workbook or your solution in the link given, and then write your name and matrix number. Yeah, and don't forget to scan this attendance form as well. So I think that's all for our lecture today. Thank you for your time and have a good day.